For more than 2 decades, 13.8 billion years has functioned as one of the few genuinely settled numbers in all of cosmology, a figure taught in classrooms, printed in textbooks, and treated with roughly the same confidence as the distance to the moon. In 2026, that number is still the figure every major space agency and every peer-reviewed cosmology textbook uses, but the confidence surrounding it has quietly, measurably eroded to the point that a leading astrophysicist stood up at a major astronomy conference and used the word crisis to describe what is happening to it. This is the story of what has actually changed, what genuinely has not, and why the honest version of this story is considerably more interesting than either nothing to see here or everything we knew was wrong. To understand what is actually being debated, you first have to understand how astronomers arrive at a number like 13.8 billion years in the first place, because it was never simply read off a cosmic clock. It is calculated, derived from measuring how fast the universe is currently expanding, a figure called the Hubble constant, and then running that expansion rate backward through the mathematics of the Big Bang model to determine how long ago everything must have started from a single point. Get the expansion rate right, and the age calculation that follows from it is remarkably precise. The entire foundation of the 13.8 billion year figure rests on that expansion rate being measured correctly and consistently, regardless of which method or which era of cosmic history you use to measure it. That is precisely where the trouble has been quietly building for the better part of a decade, and a problem cosmologists call the Hubble tension. There are 2 fundamentally different ways to measure how fast the universe is expanding. The first method looks at the early universe directly, using the cosmic microwave background, the faint, ancient radiation left over from roughly 400,000 years after the Big Bang, and calculating the expansion rate implied by that radiation's precise patterns. The second method looks at the nearby, more recent universe, measuring the distances and recession velocities of relatively close galaxies, using tools like pulsating stars called Cepheid variables and type Ia supernovae as reliable cosmic distance markers. In a universe that behaves exactly the way the standard cosmological model predicts, both methods should produce the same expansion rate, since they are measuring the same underlying physical quantity from 2 different vantage points in cosmic history. They do not agree. The discrepancy between the early universe measurement and the nearby universe measurement has grown, as of the most recent analyses, to a statistical significance exceeding 6 standard deviations, a level of disagreement far too large, according to standard scientific convention, to dismiss as coincidental measurement error. And critically, this is not a problem James Webb Space Telescope discovered. It predates Webb entirely, built up over years of increasingly precise measurements primarily from the Hubble Space Telescope and various ground-based surveys. What Webb has actually contributed to this specific debate is, in some ways, the opposite of what recent headlines have implied. Rather than deepening the confusion by introducing a wild new number, Webb's considerably sharper resolution was specifically used to rule out one of the leading alternative explanations for the discrepancy, confirming that the nearby universe measurements were not simply being thrown off by crowded, overlapping, or dust-obscured stars that an instrument with Hubble's older, lower resolution might have blurred together inaccurately. Webb closed off that particular escape hatch. It did not open a new one. The tension deepened further and in a genuinely significant way in December of 2025, when an entirely independent measurement technique weighed in. Rather than relying on Cepheid variables or supernovae, this method used the time delay between multiple images of the same distant quasar, produced when a foreground galaxy's gravity bends and splits the quasar's light into several separate paths that reach Earth at very slightly different times, a technique called gravitational lensing time delay cosmography. That independent method landed on the side of the faster, local expansion rate, the same rate the nearby universe measurements had already been suggesting. Rather than resolving the disagreement, this new, completely independent method deepened it, making it considerably harder to argue that the tension was simply an artifact of one particular measurement technique going wrong. Astrophysicist Dan Skolnick, presenting at the American Astronomical Society meeting in January of 2025, was the researcher who explicitly used the word crisis to describe where this leaves the field, a characterization that reflects genuine widespread unease among cosmologists rather than a single outlier's dramatic framing. If the faster, locally measured expansion rate ultimately turns out to be the correct one, the straightforward mathematical consequence, running that faster rate backward through the standard Big Bang model would be a universe that is somewhat younger than 13.8 billion years, with the simplest versions of that recalculation landing somewhere in the range of 12.5 to 13 billion years, a meaningful but not enormous downward revision rather than any kind of dramatic overhaul. That is the genuine, well-documented scientific story, a real deepening measurement discrepancy, taken seriously by leading cosmologists, that could eventually push the universe's age modestly younger than the textbook figure, once the field manages to determine which of the two competing measurements, or some entirely new explanation neither one has yet identified, is actually correct. It is a real crisis, in the specific technical sense cosmologists use that word, meaning a genuine unresolved tension between two independently well-supported measurements, rather than either measurement being simply wrong. What the title of this story, and a considerable amount of recent online coverage, has done with that genuine scientific tension is something else entirely, and it deserves to be addressed directly rather than left to stand uncorrected. Separate from the Hubble tension debate, an entirely different and more speculative claim has circulated widely. The proposal that the universe might actually be twice as old as currently believed, roughly 26 to 27 billion years old, an idea built around a specific alternative cosmological model proposed by a single researcher, designed specifically to explain a separate puzzle Webb has genuinely uncovered: the existence of surprisingly massive, apparently well-structured galaxies, appearing earlier in cosmic history than standard galaxy formation models predicted should be possible. That impossible early galaxies puzzle is real and worth taking seriously on its own terms, and it has been the subject of extensive, legitimate research throughout 2025 and 2026. Webb has confirmed, through rigorous spectroscopic follow-up rather than rough estimates alone, multiple galaxies existing when the universe was only 3 to 400 million years old, some of them surprisingly bright, compact, and structurally organized for objects that young. But it is important to be precise about what that actually means, a distinction one recent careful analysis of the data laid out clearly. Webb has found galaxies that look unexpectedly bright, chemically developed, or massive at very early cosmic times. It has not found a galaxy that can be shown to have spent billions of years calmly forming stars before the universe was old enough, under the standard timeline, to allow that much time to have passed. The confusion, as that analysis put it, comes from compressing several separate observational properties: redness, inferred mass, structural organization, apparent chemical maturity, into the single loaded word old, when a galaxy can display any one of those properties without that property functioning as a literal clock proving billions of elapsed years. The specific 26 billion year alternative model remains, as of 2026, a minority position within the broader cosmology community, one proposed hypothesis among several competing attempts to explain the early galaxy puzzle, not a peer-reviewed consensus, finding that has displaced the standard timeline. Competing explanations, including the possibility that early star formation was simply more efficient than standard models, assumed, or that black hole-powered objects rather than ordinary stars account for some of the earliest, brightest sources Webb has detected, remain under active, serious investigation alongside it. And none of these competing explanations has yet achieved the kind of broad, independently replicated confirmation that would justify treating any single one of them as having actually overturned the 13.8 billion year figure. It is worth being equally clear about the most recent record-setting galaxy discoveries specifically, because they tend to get folded into this same ages-changing narrative, despite measuring something entirely different. In 2026, a research team led by astronomer Rohan Naidu reported a spectroscopically confirmed galaxy, designated MOEM-ZAF-14, at a redshift of 1444, meaning its light left the galaxy when the universe was only a few hundred million years old, the current record for the most distant, earliest galaxy ever confirmed. That measurement is a genuine, remarkable achievement in observational astronomy, and it does push the boundary of how early in cosmic history astronomers can now directly observe galaxies actually forming. It does not, on its own, change the calculated age of the universe itself, because that record distance measurement and the universe's overall age are two conceptually separate quantities, one describing how far back in time a specific object can be observed, the other describing the total elapsed time since the Big Bang itself, calculated from the expansion rate rather than from any single galaxy's distance. So where does that leave the honest answer to this story's own title? The universe's age has not, in any confirmed, peer-reviewed consensus sense, actually changed from 13.8 billion years as of the moment this is being written. What has genuinely changed, and changed significantly, is the confidence surrounding that number, as the Hubble tension has deepened from an interesting anomaly a decade ago into what a leading cosmologist now describes, without exaggeration, as a genuine crisis for the field, one that could eventually justify a modest downward revision towards somewhere in the 12.5 to 13 billion year range, once astronomers determine which of two currently conflicting, independently well-supported measurements is correct, or discover a deeper explanation neither measurement has yet revealed. Separately and importantly, distinctly from that expansion rate debate, James Webb Space Telescope has genuinely, repeatedly surprised cosmologists with how mature, bright, and structurally developed the very earliest galaxies it has observed appear to be. A real puzzle, actively reshaping models of how quickly stars and galaxies assembled in the universe's first few 100 million years, without requiring, at least according to the great majority of researchers actively working on the problem, any change to how old the universe itself actually is. That is a considerably less dramatic headline than "the number just changed," but it is also the honest one, and it captures something genuinely important about how science handles a real unresolved tension responsibly. Nobody caught James Webb Space Telescope changing a number because Webb was never the instrument measuring that number in the first place, and no single observation, however striking, has yet been able to force cosmology's most fundamental timeline to move. What Webb has done, considerably more interestingly than any single dramatic number, is hand the field a genuinely deeper set of open questions than it had 5 years ago, about exactly how the universe's earliest structures formed, and about exactly which of two disagreeing measurements of its expansion rate deserves to be trusted. Questions, serious. Researchers are still working through in full public view, with the actual answer still, honestly, unwritten.